In this topic, we will discuss about the composition of concrete. There are four basic ingredients in concrete: coarse aggregate, fine aggregate, cement and water. Coarse aggregate is used as the body, fine aggregate is used as the filler, cement is used as the glue, and water is used as the activator and the lubricant. When we mix cement and water together, they react with each other and make the concrete harden. So coarse aggregates and fine aggregates will bond together and make the hardened concrete structure. This reaction we call the hydration reaction, and we will learn it in future topics. And also there are in some situations we have to add admixtures to improve properties, and also we have to add air entrain agents to build air entrained concrete for specific applications. We will be discussing these topics in later stage. Cement is the binder in concrete which binds the aggregates together. Cement used in construction are usually inorganic, often lime or calcium base. So this inorganic cement we can divide into two categories: hydraulic and non-hydraulic. Non-hydraulic cements are used when we do construction in wet conditions or underwater. They are not reacting with water and get hardened. Instead, they react with some other elements like carbon dioxide. Hydraulic cement is the cement that we mainly use in constructions. So Portland is an example of hydraulic cement. Portland is a trade name, and we are vastly using Portland cement in construction. Let's see the Portland cement production process. So Portland cement production process has many particle size reduction steps: crushing, milling, and also there are many mixing processes and homogenizing processes, and also we have a kiln to heat up and make the clinker. So we'll look at these steps in more detail. Production of Portland cement start with two basic raw ingredients, mainly limestone and clay. The first step is mining these raw ingredients, and the second step is crushing of raw material. The limestone is crushed in a jaw crusher and impact crusher with mixing of clay to reduce the particle size below 50 millimeters. This crushed raw material called the raw mill. Third step is drying, grinding and homogenizing. The raw mix high-grade limestone, sand and iron ore are fed raw mills to drying, fine grinding and mixing. Output from these mills are called the kiln feed. The next step in Portland cement production is clinkerization. In this process, we make clinker by pyroprocessing. That means we heat up the kiln feed to a very high temperature to bring chemical and physical changes. The preheater kiln system consists of many equipment such as multi-stage cyclone preheater, combustion chamber, racer duct, a rotary kiln and grater cooler. In the preheater, the kiln feed is preheated by hot gas coming from the combustion chamber and the rotary kiln. Then the preheater kiln feed is partially calcinated in a combustion chamber and racer duct, and then completely calcinated in a rotary kiln. So during this process, clinker is produced. Clinker is mainly consists of four crystalline phases. They are the four main crystalline phases in the cement. So they are C3S, tricalcium silicate, C2S, dicalcium silicate, C3A, tricalcium aluminate, and C4AF, tetracalcium aluminoferrite. So these four components are very important. They decide the properties of cement. We will be discussing that in later stage. Step 5 is cement grinding with gypsum. Clinker and gypsum for ordinary Portland cement grind in a ball mill grinder and store for packing. Gypsum is useful in cement to control the cement hydration, so it prevents flash setting of cement. Let's see different types of cements. There are 5 principal types of Portland cement classified by the American Society for Testing and Materials, type 1 to 5. Type 1 is normal Portland cement, which we can use for general purpose applications. Type 2 is modified Portland cement with a better resistance to alkali attack and produce less heat of hydration. Type 2 is suitable for use in structures such as large piers where we need to control the heat of hydration, and drainage systems where groundwater contains a moderate level of sulfate to prevent swelling of concrete due to the sulfate reaction. Type 3 is high early strength cement. It provides 190% of type 1 strength in 1 day of curing. For type 1, it takes normally 28 days to achieve its compressive strength, but type 3 reacting faster and get hardened faster. However, type 3 produces 150% of heat of hydration of normal cement in first 7 days. We can use type 3 cement for applications like repairing a busy highway, or when we are constructing high-rise buildings, or we do concreting in cold weather. The reaction of cement and water is an exothermic reaction. That means it produces a huge amount of heat. There are some applications where we have to control this heat production. So type 4 is low heat cement. It produces only 40 to 60% of heat production by type 1 cement during the first 7 days. However, its strength is only 55% of that of the normal cement after 7 days. It is produced for use in massive structures such as dams. Type 5 is sulfate resistant cement. Cement, when it reacts with sulfate, its volume is expanding. So to prevent that, we have to use type 5 cement. When we do constructions in contaminated lands, or maybe in sewer constructions, the cement can react with sulfate in the contaminated environment, so we need to control this sulfate reaction. However, its 7-day strength is only 75% of the normal cement. This is another classification of cement. Here, without using numbers from 1 to 5, we are using abbreviations. General purpose cement type GP, we use it for general purpose applications. General purpose limestone cement, which has a percentage of limestone without burning it to clinker, that we call the type GL. We use this for rendering, and it is cheaper than the general purpose cement. General purpose blended cement is produced by blending different types of cements together. We call it type GP. Special purpose cements are high early strength cement type HE, low heat cement type LH, sulfate resisting cement type SR, and shrinkage limited cement type SL. We can achieve these properties by having different proportions of the 4 main ingredients in cement: C3S, C2S, C3A, and C4AF. We will discuss this in later stages. And also we can add additives to cement to achieve different properties. Also, the cement particle size is contributing to different properties. We discussed that cement is the bind in the concrete mix to bond the aggregates together. However, cement need to react with water to make this bond. So water is required in the concrete mix for several purposes. Principal among these is to provide the moisture required for hydration of the cement to take place. The amount of water in a mix affects the plasticity and the workability of plastic concrete. We will discuss these topics in later stage. In terms of water quality, almost any water suitable for drinking will be satisfactory as a mixed water. However, we may not be able to use water with drinking water quality to mix concrete all the time. Organic material in mixed water tend to prevent the cement paste from bonding properly to aggregate surfaces. Alkali or acid in mixed water may react with the cement and interfere with hydration. Seawater may be used for mixing concrete, but its use will usually result in concrete compressive strength 10 to 20% lower than normal. However, seawater should not be used for pre-stressed concrete, where the pre-stressing steel will be in contact with the concrete. When water quality is in doubt, it is recommended that trial mix be tested for setting time and 28-day strength. Herewith we are finishing our topic, subtopic 2, and we will move to the cement hydration.